after the post DFT, post silicon, we can say. So today's agenda, we will cover with the following topics, why DFT, what DFT, what are the DFT insertion flows in place, how the MBS insertion is happens, then what is the scan chain operations, scan insertion flow, certain issues, challenges, and also DRCs, and how we can fix those kind of the issues during DFT insertion. Another structure we can say is OCC, which is clock controlling block, which is very important while we are doing the edge speed testing. Then the main thing we can say after insertion of scan insertion, the next thing would be ATPG flow. So automatic test pattern generation. So here we will generate different kind of vectors in order to test the chip. Another certain architecture nowadays people are in SoC is using is IJTech. So I'll little bit cover on IJTech as well, and few advanced DFT techniques which nowadays we are implementing on different SoCs and based on the various application of the chip. And then will be the Q&A session. So this is the agenda of today's talk. In case if you have any questions, you can anytime you can ask me, or maybe we can cover it in next in the last. So okay, let's start with our DFT agenda topics. Okay. Before why and what DFT, I think we need first I should cover just a second. Why is the slide? Before why and what DFT, let me start with ASIC design flow and where the DFT comes in the picture. So initially, most of the people might aware how the flow is going on. So initially, any of the chip it start with some specifications, what kind of the applications it is intended to design the chip. Then what is the chip architecture, design the microarchitecture, verification plan, DFT plan or architecture, even in the post DFT, I mean it's a PNR stage, how it is. So initially everything it start with specification. So once the specification is defined, the RTL design start with the designing the block level things, different blocks they start doing implementing using the Verilog code. And functional verification team starts verifying the RTLs by different test cases using the system Verilog and other UVM environment stuff. So this is all about purely functional verification, we can say. Now, what is the next? So once RTL is at certain level, the next thing would be synthesis. So here, how the synthesis, what happens? So synthesis, RTL, all the RTL is integrated, and we can say it is converted into the, or we can say map with the lib cells, what a standard cell is used, and RTL will, we can say, converted into the net list. So here main the concern point we can say is a power, area and timing estimations we can identify at this stage initially. So once the synthesis is done, so we can say our netlist is ready for the next step, we can say. So the next step would be the DFT. So in DFT, what happens? What we need to do? So once the netlist is ready, so we need to make this design testable. So in order to make design testable, the certain architecture or certain flow or certain steps we need to perform in order to insert the DFTs. For example, we can say JTAG based structure, M based insertion for the memories to be tested. Then the other rest of the logic we can we can cover in the scan insertion, and LECs also needs to be performed, and test point insertion in order to get good coverage, good amount of the coverage. If some certain, if we miss in some of the areas in the design, then like we can do the test point insertion in a DFT stage, and we can get the higher coverage. So this is the very important stage, like after synthesis in for the DFT. Once the design is DFT inserted ready, the next thing would be physical design step. So it's a, we can call it as a PD. So now the netlist needs to be handed over to the like PD team. They are start working on the like floor planning activity, placements and route, like CTC, clock tree synthesis, verification. So here, like you can see all the pictorial view, like how it's like we try to map with the like what are the steps needs to be do, what are the steps we are performing. So here main thing is in PD is a point in which we can relate. The very important thing is STA, like static timing analysis. So once the STA is done, then other like parallelly the placement and planning activities and also verification activities starts. Once the PD is done, now what? So now design is ready to be tap out. But before the tap out, what we need to do is a DFT. We need to do pattern generation, vector generation, it on the gate level netlist, the GLS netlist. So here we need to generate the different set of the vectors for ATPG, M based, we can say L based, JTAG, and also like standalone some IPs are there in our design. So for that different set of the test vectors like we need to generate. Once the vectors are generated and it is verified with simulation, gate level simulations, we can consider to be design is tape out ready. So once the tape out is done, like GDS2 file is given to the like ATFM, and they start some manufacturing the chip. So there are certain steps in manufacturing as well. I'm not going into detail, but it start with sand to silicon. We can say we need to generate ingot, and after ingot, the wafers are sliced, and on the wafer, different fabrication processes happens, and ultimately, like we can say, the chip is ready to be tested. So the next one would be silicon bring up. Once the wafer is ready, the next step is a silicon bring up. So on silicon bring up, what happens? So we have like whatever the generated patterns we during the pre-silicon phase before the tape out, those patterns are actually tested on AT environment on the different wafers. So based on that, certain analysis needs to be done on AT, like our how the patterns quality is there. That is also needs to be ensured. Another thing is yield analysis, then the failure analysis, and if something is failed, then also we need to do the diagnosis. So we can say the DFT rolls in ASIC flow at three different stages. So once the synthesis is done, then each and every stage in a design ASIC flow, the DFT comes in the picture. So this is the we can say overview of like ASIC flow, as well as we can say where the DFT roles comes in the picture. So now here you can see this image with different colors. This is wafer map image. So the different color set, it indicates the how the passing regions are there, and based on the failure needs to do the diagnosis, and even different analysis needs to be performed on in order to make what is the reason behind those failures. Okay, so now I think we should go with like why DFT and what DFT. So why DFT? So there are possibilities of error. We can say the technology node is continuously shrinking, and nowadays people started working on 3 nanometer technologies. 3 nanometer and 5 nanometer technologies chip is already out in the market. So when the technology nodes is shrinking, there are more chances of manufacturing process. During the manufacturing process, there are more chances of defects. And even we can say another thing is the functionality is too much increase. Specification, there are more functions are increased nowadays in a chip. So we can say the number of transistor is very high in our design, and the sizes are already, like as I said, it's decreasing. So what happens due to this, the chances of errors or occurring errors are increased. And we can say the fabrication process is always good, but it's not prone to, we can say, defect free. So there are certain limitations also in the fabrication side, and due to this micro technologies, there are defects are occurring more now. So now how once we have, like, we can say, defects, so what is the next thing? Like, so defect can represent the different certain faults in our chip, and it shows, we can say, based on testing, we can say it checks correctness of the manufactured chips. So once we have a certain test to perform on the chip, based on what is the outcomes, we can identify how the manufactured chips are, like, we can say the quality of the manufacturing chips. So we can normally sometimes the error, or maybe it's due to pattern as well, or maybe sometimes it's real defects. So this is very crucial step, we can say, when we are doing the debugging in the post silicon. Once the silicon bring up is happens, how we need to identify those manufacturing defect, and we need to prove like it's like a real issue, or like, or it is only a pattern failure or vector failure. So vector is not like as expected. Now what is DFT?
Uh,
So yes,
Bhavesh, shall I interrupt you?
yes,
Uh,
sure.
shall I able to quote one statement that verification is normally used to identify the bug present in a design,
Correct.
while DFT is used in order to identify the
A
bug,
defect.
a defect, a physical
Yes,
defect present in the manufactured chip. Uh,
correct.
am I right?
Yes.
Yeah.
So normally verification, yeah, even before sending all the patterns or vector generation, we used to do the verification in pre-silicon environment as well. So, but in pre-silicon, what happens? Our design is already like, it's a virtual design. It's already in our virtual design. It is, and tool is generating whatever the design is available. But when it is actually implemented on silicon, there might be certain issues, right? Because of the manufacturing process. So ultimate our goal is we need to deliver the fault free chip to the customer. So for that, certain step we need to do now. Okay, am I given the answer to your questions, or should I
No, no, no. Fine, sir. It's
okay,
I got your
okay. Now, what is DFT? So there are certain techniques and set of rules, we can say, uh, we need to follow during DFT insertion, which ensures the quality of the device. So the quality of the device is very important, because uh, I remember like a few years back, there was some bug in a chip. or even nowadays also I am facing, I'm not giving any name, but of any customer, but let's say if some customer is using their already products in a market, and while let's say we are using some handset or some chip in our room, and we are facing continuously, let's say, Wi-Fi related issue. One of the example I can take. So my Wi-Fi is every time disconnected, or something is happening, it's not properly as expected, it's not continuously we connect to the design, connect to the internet, we can say. Then like certain issues needs to be debugged, and based on the customer complaints to the vendor, they are starts like diagnosing what is the issue. And at that time the cost of this testing, we can say, it's too far. There is a rule of tenfold in a, so it's a tenfold, it is increased at every stage. So if it is any of the defect we can identify in early stage, then it would be good. Otherwise, it will like create a lot of loss. So there are two certain, only two properties. The whole DFT is works. One is the controllability and observability. What do you mean by the controllability? So controllability means how easily we can cover certain nodes in the design. So we have like n number of the gates. Let's say nowadays we can say the chip I'm working is 45 million registers, or 45 million registers only. So we can say 45 into, let's say, 10 or 10 or 15 times certain gates are there, logic gates. And if I wanted to test each and every node of this gate, so I need to have some vectors. So how easily I can control each and every node from the input side? So I can place certain values, 1 or 0, to the specific node, and how I can observe on output side. So these two things is very important, like when the DFT comes in the picture. So testability is equal to, I can say, controllability plus observability. So these two properties, the whole DFT is work on, we can say. Okay. This is just try to I'm showing.
Sir,
Okay.
may I
Yes.
ask the question?
Sure.
Can you please elaborate the controllability and observability difference in detail? What is
Okay.
the difference between these two?
Okay. For example, let me show any circuits. Okay, I'll take this circuit as my reference. Let's say this is one inverter. It is placed in my design. Okay, so there are n number of the cells around this gate, and my chip has n number of IOs, input and outputs. Okay, so when I'm saying this is very internal to our logic, from input pin to this NOT gate. If I wanted to test this NOR gate, NOT gate, what I need to do, if I'm here putting, I need to put 1, I'm expecting 0 here. But certain, due to manufacturing, this node is, suppose, let's say, stuck it to 0. So it will always give 1, irrespective of, let's say, if I am putting here 1 also, it will give output like 1 only. So what happens, if I wanted to control, if I wanted to place some value at this node, either 1 or 0, so how I can place? So normally what happens, like in a scan, uh, how easily from input, from PI, we can say primary input to this pin, if I'm able to successfully place the 1 and 0 at this node, and then we can say this node is controllable. Okay, but now if I'm suppose, let's say, I'm easily place 1 and 0 at this point, but output of this node it should be also accessible to the output of the chip. If it is not able to properly observe, then we can say the observability of this node is not good. Or I can say I'm not able to measure the output of this specific not get it output of the chip. So the controllable and this is the observable output, we can say it should be observable. So I could in other terms what I can say, I am not able to generate any patterns or any vector. I am not finding the such vector which can test this not get. So when I'm saying I'm not able to generate any vector or pattern, we can say the controllability and observability of this not get is not good. Hello, madam. Yeah.
Yes, sir. Yes, sir.
Any other questions on this, or are you getting your answers?
No, sir. Getting. Thank you.
Okay. Thank you. So now what happens? Like let's say this is the behavioral model of like behavior when we are writing the Verilog codes. This is a higher level, very higher level, and we can say this is the like CMOS level, or we can say structural, very CMOS structural level. So we will go through like during the design different stage. Like this is RTL level, we can say this is schematic PNR, and the final we can say it's a silicon level. So what manufacturing test does? So manufacturing test like try to compare the predicted behavior of gate level design to the actual silicon behavior. So ultimately our goal is to test the silicon, but here we can't do directly any 1 and 0. So we will try to model the value or vector in such a way that so it will directly reflect, or we can say predict the behavior of this silicon, either it is like actually the working is expected or not. Another thing we can say manufacturing test, this proves that the chip was built as designed, but it doesn't mean that the chip was designed correctly. So this two statement is contradictory because there's sometimes what happens, the design is wrong. If design is wrong, then the manufacturing test is also wrong, but it doesn't mean like our chip is faulty, because it's a functionally issue, functionality is not good, or maybe something is missed during the RTL. So if something is missed, then already like the design is like we can get silicon in such a way that only. So manufacturing test we can say is a kind of the structural testing. Okay, so here like try to put some defects, how some snaps of the defects, and what kind of the issues then what happens to the silicon. Defects here you can see some excessive amount of the material which is placed on like different wires, or we can say parallelly 3 to 4 wires are going on here, and some non-conducting material it is like placed excessive during the manufacturing defects. So this can cause like open the like these 2 or 3 wires, and it certainly creates some problem to the higher level. It may like what we can say what the word I can say, the functionality of the specific area or certain region in a design. Another defect is like this is the conducting material. It is placed in between 3-4 parallel going wire, and it becomes short. So this short ultimately can reflect to the, let's say suppose this is the connecting wire of some gate or some AND gate or NAND gate or any other logic. So it may be short to the ground, or it may be connected to the VDD, and accordingly that it can reflect to the stucket fault or maybe other faults. So this is another like example of defects. So here like small crack like connection like between 2 parallel going wires, and it becomes some resistive sort in between. So the cross coupling is happening in between these two parallel going wires, and it create again problem. So this kind of the manufacturing defect, like we need to identify with DFT vectors. So here the one of the example of the ESD. So due to electrostatic discharge, when the test where the silicon comes under the very high voltage testing. So there are certain tests on post silicon like ESD test. So for that I'm very like rigorous recursively, like week or 24-hour continuously they are giving some voltage and voltage stress to the specific chip, and to see like how the chip is behaves. So, and if something is like this kind of the issues are occurs, then we can easily detect like during those kind of the testing. So there are manufacturing defects. This kind of the defects are occurs. And now the thing is how we can infer this defect. So there are three things we can say in the DFT. Three words is sometimes people are confused with these three words: defect, faults, and errors. So what is the difference between these three? So defect is actually manufacturing defect, the problem we can say during the maybe excess amount of the doping or certain impurities are added, and this kind of the defects are occurs in during manufacturing process on silicon. Now what is the fault? So when the defects, some defects are occurs, let's say here some defects are there. So ultimately this is, let's say, gate is connected to we can say ground. This is ground line is going on, and this is the gate of one of the chip, one of the gate. So when some connection is happens, we can say the gate is shorted to the ground. So here I try to draw some analogy, like let's say the gate A is connected to the directly ground, some resistance, some like we can say resistive ground. What happens now? So when we are applying this first three vector, because this is a NAND gate, so any of the zero input output should be one. So when we are applying these three vector, we are not able to identify is there any faults on output side. But when I'm applying the 1 at that time, ideally my output should be 0, but A is already stuck at to ground. So we can say the stuck at when A and B is 1, C is equal to 1. So error, this output we can consider as an error. So error is a wrong output signal produced by defective or faulty circuit. So when I'm saying error, like when the vectors are available, when I'm delivering to the tester, on tester they are testing those vectors and they are giving some outcomes. So those outcome I can consider as an error, and based on the error I need to identify what is the reason behind those failure. So defect we can consider as actual. False we already targeted actually initially, and based on that it's a kind of representative of the defect. So initially we are identifying if something like we are when we are generating the vectors, like we need to target the certain faults like stuck-at fault, transition fault, path delay faults, IDDQ faults, cell aware. There are n number of different like bridging faults we need to target. So patterns or vectors are generated accordingly only. So we know like these faults we are targeting during DFT insertion, and based on that when we are delivering to the silicon ATE, and what if something is failed, we can get the errors, and based on the error again we need to identify what is the defect.
So, Bhavesh sir.
Yes.
So some sort of mapping table is required over here, which can map the physical defect with the logical fault.
Mapping table in the sense
Because see, we will have to now convert all different type of physical defects in terms of logical fault, which can represent the defect, like stuck at 0, stuck at 1. So some sort of mapping is required.
No, normally what happens, what my experience here tells, let's say initially we already know before silicon came, what we need to do here is we already know we are targeting stuck at faults. Okay, for example, stuck at faults means the how the tool, or we can say environment, generate the patterns is based on, let's say this is AND gate, so it will try to cover each and every nodes, right? And our vectors are generated in such a way that it will try to cover each and every nodes of this design, and so our patterns already have information of each and every stuck at nodes. Okay, now what is the next thing? If something is fail on ATE, what we need to do, we need to identify, we don't know actually from error log where the in the chip, in the full chip, where is the failure.
Okay.
So first, this is very difficult to identify the location first, where the in the full chip entire SoC, where is the failures occurs. So initially we want able to identify it is failing for the specific NAND gate. At least we can get some register info. So output of this NAND gate, it is propagate or captured to the specific flop, right? So we can get those info only. So those info we can normally either we can provide to the specific people, or maybe some designer, or parallelly we are trying to identify like what is the reason behind this, because this flop having many downstream logic, because this is not only one NAND gate, so there are many other logic, combo logic is there. So we need to identify either this is the like suspected gate where the failures are there, and based on this like if this is, and also not based on only one chip, there are n number of chip needs to be tested, and if all the chips having similar failure, then we can say either it is a issue with some pattern, or it's maybe not a manufacturing defect actually, that those kind of also possible. So but we can't directly say if what is your question is mapping, right? So we can't directly say stuck at 0 means the sort between these two. It might be some different issues also, because where the sort is happened, that is also important, right?
Okay.
So we directly can't map. So for that, there are certain analysis they need to do, and we need to provide feedback to the TSMC for the process improvement as well. So those based on those consideration, they'll try to focus on those area why those kind of the issues are occurred. So that kind of the like 2 and 4 analysis is going on like in during post silicon.
Okay. So I got your point. In the sense, using DFT, we can able to identify the fault up to
Yes.
gate level only.
Yes.
We cannot able to identify the
Yes.
defect at a silicon
Defect.
level.
Correct. So those information, at least we can provide it to the TSMC, so they can check on actually this kind of they have like images and their microscope and all, so their research team can check on that.
Okay, got your point.
Yes. Okay, I think here no need to cover this one because most of the things I covered. Where comes in the DFT? Okay, should I? Okay. Now DFT insertion. Insertion flow, because in ASIC like we have different flow at different stage. RTL is also flow. Synthesis has its own flow. DFT has its own flow. So certain steps needs to be performed. So on the now DFT starts with, as we know, like from the synthesis netlist, and now DFT preparation. So here also it's a kind of specification for DFT insertion, we can say. So we need to be prepared for the DFT insertion. So what kind of the criteria or specification or we can say certain configurations needs to keep in mind when we are starting the DFT. First is, we can say how many pins are available for the DFT insertion, because there are many pins in our design. Let's say one SoC has 250 pin or more than 450 pins, but for DFT, how many available? How many input and output I can use out of those pins? So those things I need to define. Another thing is, what is the how the chip requirement? It's a power hungry, or it's a like low power design, or sometimes what happens, area is also important, because certain limitation is there, so we can't go beyond those number of areas, millimeter square. So those kind of the considerations we need to keep in mind, and we need to architect the DFT first, and we need to identify the which architecture I should use and what are the things I need to keep in mind. So those like preparation I can consider in terms of the DFT preparation. So once everything is defined, how, okay, one more thing I miss is memories are also very important. So how many memories are there in design, and what is the plan for memories also, how I can test the memories. So those things like comes in the DFT preparation. Once the DFT preparation is done, next item is M-based insertion, memory based insertion. So M-based insertion is also its own flow to insert the memory on the synthesis netlist based on our DFT preparation. Once M-based insertion is done, we need to do scan insertion. M-based insertion is only for the memories to be tested, or how many memories are there and how we can test. For that, we need to do the M-based insertion, and the scan insertion is for the remaining all the logic. So once the scan insertion is done, what the next thing is for us is the ATPG. So pattern generation, vector generation, automatic test pattern generation. So ATPG has also its own flow. And once the ATPG is done, next thing would be simulation. Once M-based insertion is done, we need to do the verification as well at this stage for the M-based patterns, M-based vectors. Now, but during the optimization and insertion in those stages, like when we are doing post synthesis to M-based, we need to do the equivalence check, formal verifications. So this is very important stage also. Here we need to check because once we are optimizing and inserting some logic in the actual synthesis netlist, it should be logically it should be equivalence. So if something is missing, so we can easily identify or catch here in formal verification stage. Similarly, once M-based insertion is done and we are doing the scan insertion, so again netlist is modified and updated and optimized, and area consideration, power consideration, there are certain optimization is happens. So again the netlist is new, so we need to do again equivalence check between these two. Even also we sometimes we are doing equivalence check between post synthesis and scan insertion as well. So this is to ensure like our design functionality is not modified, because DFT is such activity, we can say it's only comes in the test mode only, and the functionality should not be changed anyhow in a design, otherwise it's everything like great problem.
Sir,
So
one question is there in the chat box,
mhm.
asked by Yogesh Tiwari, sir.
Oh, okay.
Can scan insertion be done before M-based insertion?
Good question, but no. We can't do scan insertion before M-based insertion. So first, because there are certain things nowadays. Okay, uh, there are n 2-3 reasons, but first reason I would say time to market. time to market in the sense like we have very less time to do everything from RTL to PD. So what happens here? Even though I mention here MBC insertion, but nowadays MBC insertion is done directly at RTL. Okay, so once it is done at RTL level, directly after on the synthesis netlist, I need to do the simulation. So time is very we can save the time, iteration time. Even we can say, like, let's say every time synthesis netlist would be changed, because RTL is also changed when during the design phase. So what happens when the RTL is changed, synthesis netlist is updated. Synthesis netlist is updated, and memory doesn't change normally. Memory is fixed in a chip. Once chip specification is defined, memory normally it is fixed. It's very rarely it is changed. So that what happens, the whatever the embedded logic is inserted during those design stage, it would be fixed. No need to change, and it will save a lot of time and human efforts, and even we can say like error-free execution also. So only we need to do the simulations at that stage. So this is one of the reason. Another thing is memory, like we have like SRAM, ROM. So if we wanted to test those memories, we can't go for the functional verification, because there are n number and another thing is we can't do scan insertion on the memory, because otherwise it will uh, what we can say, it's like if we insert the logic inside the memory, this is not viable solution, and even on the output of the core logic as well. So memory insertion, once it is done, so we can fix those timing constraint as well, or SDC, there are delay constraints. So timing related issue also we can avoid. Another reason, the third one, what I can tell is in M based, I think this is yeah, hi Yogesh. Yeah, do you have any other questions in this, or any other things in your mind? So I can, like, as of now I don't recall any other points what I can say.
No, sir. Now he got your point.
Yeah,
Okay.
it's clear. Thank you.
Yeah.
Sir, one
So,
another
yeah.
question. That what is the percentage of area overhead due to this DFT in a given design? Typically,
Normally it depends again design to design how many so mainly what my experience says here, most of the area overhead is due to MBIST. Scan doesn't take much area, because it replaces only flop to scan flop. But in MBIST, what happens, there we need to do explicitly, we need to insert the tab controller, then MBIST controller, BIST controller. Then it has like BIST controller is also not directly communicating to the memory, so there is some interface logic is also there. So most of the logic like area overhead by the MBIST. And in my one of the small chip, last chip, the due to memory BIST, the area overhead is 5% or something. Okay, 4 to 5%, and around 1.5 to 2% for the scan only. 1.5 full chip area, I can say. But it was a small chip. But when it's bigger chip, the number is very 10% or something, I guess. 10 to 20, 15 also it's possible, but I think not more than that.
so once this DFT is inserted, it will be there, right, up to the fabrication process.
Yes, logic is always there,
Right.
and only tested once.
Okay.
In a whole lifetime cycle. Okay, so few step here in MBIST insertion flow. So now like what MBIST? So when we wanted to test some memories, like we need to have MBIST into the place, MBIST insertion, MBIST logic into the place. And nowadays it's very important because the functionalities of the SOC is very increased. There are more memories are now in a like in a design. All the memories like have different at speed frequency, working frequency, and to testing all those memories, we can say it will. We need to do MBIST must. We need to have must MBIST. So yes. So testing all the memories sequentially would take long time. That is another point. Okay, later I will come to there. Okay, chip area reduce compared to allocate individual MBIST control. This is also another. Okay, this is now advanced. Now if when okay before this, what I can say, going to this. Okay, what are the parameter consider? This is very first question should in our mind when we start MBIST insertion. So what are the parameters I need to consider during memory grouping? Grouping is very important here when we are doing the MBIST, because let's say in my chip there are 100 memories, and 100 memories, few of them are RF memory, some are RAMs, and ROMs are also there, OTP is there. So different kind of memories are there. So once those memories are there, I need to identify like how many types of the memories are there. Accordingly I can make a plan, and how another parameter need to consider is frequency of those memories. So certain memories are work at 10 megahertz, certain memories are work at 50 megahertz, certain memories are work at 100 megahertz. So I need to identify those kind of the memories as well, like it's what frequency those are working. Another thing would be size of the memories. So how many outputs are there, like it's a 20 by 32, 1020 by 1024 by 512, like different size is also important. And the last one is location, where the memory lies. So where the memory is placed in a chip, in which area, because let's say my chip size is 10 by 10 and on this chip like we have 2 RF, or we can say I have 5 same kind of the RAM, and also 5 RAMs are working at the same frequency, but one is placed in a top left corner and another place in a bottom right corner in a memory, in a chip. So those kind of the analysis also we need to do. So I can't use the same controller for the bottom right and top left corner of the memory. So I need to have different controller for the same. So here like there are certain stage or step, we can say it's a mentor flow. Normally we are using mentor test and base flow in order to insert the MBIST, and during this is some checkers here needs to like design will check for the like how the clock are there, then is there any violation, clock is coming fine, reset is coming fine, then we need to do the plan. So plan is very important stage in a MBIST insertion. So here we can plan everything, like how many controllers I need, how many step I need. I either what is my important for me, either test time is very important or area is very important. So everything I can design here. Here power is also I can identify how much power I should. It's a power hungry or I can flexible with power. So those things we can try out in this stage. Then in assembler Based on this, everything is checked and everything done. Then assembler will generate the different RTLs for those controller, and its synthesis is the same with the actual design. And then we need to do the verification of those logic. So here during the verify also we can this is the last stage where we are writing out the patterns and vectors, and those vectors we need to simulate in our gate level simulation environment. So once those vectors are written out, so those vectors are generated based on the different algorithms are used during the memory base. So here one of the example it's put is modified algorithm test sequence. So there are March algorithm, A-Smart algorithm, checkerboard algorithm, A-Smart checkerboard algorithms. So which will generate which will try to cover different faults and different patterns like it will try to cover all the memory related faults in a pattern. So it's automatically will generate. So here like a simple diagram is capture here. This is one of the memory, and this is the BISC logic here, everything. So here we have FSM controller. It will generate the data and address and control bit to the test to the like fit to the memory, and accordingly whatever the outputs it again compare here, and output of this comparison again goes to the tap controller, and from the tap output we will measure final on ATE. So this is the flow we can say. So here like this logic is placed while we are inserting the DFT MBIST. So here any questions on MBIST side? Okay. Scan flop. Okay, I think most of the people might aware. Okay, so this is the normal design we can say, and this is the sequential elements are placed in our design. So we are not during the DFT insertion we are not inserting any new flops for the we can say controllability and observability, but we are using the existing the sequential element, and we can replace with the mux, or we can say this flop we will convert into the scan flop. And once it is converted to the scan flop, we have control of data in and data out of this flop. So what we can do, the idea is here we have another input we can call as a scan input, and the mux selection line is controlled by the shift enable. So once either we wanted to shift the data to the output side, so scan in and scan out is my we can say DFT pins, I can say. So is in the previous slide I discussed, like I need to identify how many scan in scan output I have for the DFT. So accordingly in a design I can do the scan insertion. Okay, I think okay, let me go through this scan chain operation quickly. We have 3 flops in a design. All 3 flops are stitched in a one chain, and this is ASI and this is SO, and this is scan enable. So, or we can say shift enable. So it will enable the shift. Either it is shifting is happening or it is capturing is happening. So once the clock is arrived, let's say scan enable. Let me go to next. Okay, scan enable is 1. Scan enable 1 means it will shift mode. So data, whatever the data placed into the SI pin, it is shifted to the flop. This is D flop register and out, and it is moving towards the SO. So each and every clock cycle data is shifted to the out. So let's say I need a 3 clock cycle in order to get the shift out the data. So let's say 1 is 1 0. So I need to insert 1 first. So what happens here? 1 is going first clock cycle. Here you can see the parallelly the clock cycle as well. Another clock cycle, the 1 is shifted out to another one, and 0 is shifting to the first flop. So this way, like the shifting is happening. So why we need a shifting actually? The shifting will fix the value at the internal node. So ultimate our goal is to test this logic, not here anything. So our goal is to test this logic, combo logic. So if, as I said, like this point is controllable or not, earlier like the question was there, right? So here by placing this 1 and 0, if I can put here successfully 1 and 0, this is very simple example, but sometimes what happens here, keeping 1 is very difficult. But so that's why like here like 1 is placed, so I can, if I put some a and b value here, this is, I can consider the primary inputs. If I put anything here 1 1, let's say here I kept 1 1, so here comes 1 and 1 1, it is 0. So 0 is again came here, but currently we are in shift mode, so we are just placing the value to the respective node. And when we are giving when we are providing the primary inputs, it will start exercising the different nodes. Now what happens if shifting is done? My next thing is capturing. So data, whatever the data is, like when shifting, during the shifting, what happens, we have placed these values where the output queue is going. But after that, what we are doing, we wanted to test specific node. So when I'm giving the 1 1 data here, okay, so this path has some values, but those values are coming here, but it is not captured actually on output side. So this value, if I wanted to propagate it SO, or maybe this value I wanted to propagate SO, I need to have capture. So when I'm putting the scan enable now, shift enable 1 to 0. So here scan enable 1 to 0, and I'm giving the clock pulse. The data will, whatever comes of the output of this logic, it will capture into this flop. And once the data is loaded to this flop, now next thing would be I need to shift out to the output side. So yes, so again I need to have 3 cycles to keep those new data out. So, and those output like it will stored in some file, we can call it as a pattern file, and based on that like we can verify actually this behavior on silicon. So either our data output is coming as expected or not. If something goes wrong, like it will create error, and based on error we need to identify what is the failure reason. Scan insertion flow, MBIS inserted netlist, read library. So now scan insertion starts after the MBIS. Once the MBIS insertion is done, the next thing would be the scan insertion. So scan insertion, what happens? We know what we need to have. So we need to have like libraries, scan inserted netlist, and scan configuration. So as already I said, scan configuration is again here very important parameter. So how many IOs are there? How many scan clocks are there? Because in the previous slide we can say here we have only one scan clock. So if let's say we have n number of scan clock, 1 2 3 4 in a design, so how many clocks we need to have for the DFT purpose? Because functional clock always there, and this is the scan clock. So those things we need to identify first, and based on that like we need to create architecture. Then how the reset is controls. So like each and every flop have reset. So reset might be coming from either it was directly coming from the top level, or it is generated through some logic. So those scan reset also I need to define here. Once everything is in place, then again like certain parameter related to the scan insertion, scan related parameters, compression techniques, which compression techniques I'm using. Compression, maybe I can talk in a last like what are the techniques could be try. So related to those parameter, clock mixing, either I wanted to do clock mix or no mix, full scan I wanted to implement, or partial scan, or maybe some compressed techniques I wanted to use or not. So those things will need to define in scan configuration. Once scan configuration is done, I will do for the preview DFT. So once preview DFT, what it will do, it will try to identify the checks, pre-checks, we can say. It will give the reports, how many chains could be created, how many inputs, whatever the configuration we set. Based on that, either we are getting is expected result or not in different modes, test mode. Once preview DFT is done, then it is the next stage would be pre-DFT DRC check. So here a tool will check for the like clocks, reset path, sequential elements, how many non-scan flops are there, is there any tri-state rules are there, X rules, X propagation is related to the X propagation, is there any rules? So is there any violation? It can print here on the pre-DFT DRC checks. So some of the DFT DRCs we must have to fix, and some of the like DFT we can eliminate, or we can go forward with those also. So once this DFT pre-DFT DRC checks are done, or all the DFT are resolved, then we can start inserting the DFT. So in insertion, what happens? The tool will stitch everything, whatever the configure here, in one chain, and it will generate the final. It will create the compression logic, hard macro. It will create. Then stitching will happens, and it will. We can say we can write out the final DFT netlist after this insertion stage. And after that inserting DFT, again we need to do the post DFT DRC checks as well again. So here pre DFT DRC checks and after post. So after insertion, if something is like some rules are or some optimization and many things is happens during insert DFT. So is there anything like suspicious activities, or we can say something is missed still, then we need to check here post DFT DRC. Sometimes we are not checking post DFT DRCs, but those again we need to check on ATPG. So once post DFT DRC is done, I need to, what is my output of the scan insertion? Now my question is, what is my output of after the scan insertion? So there is a like scan insert rate done netlist and SPF. I need to do. I need to write out the SPF. SPF means it's what we can say. It has like certain procedure to generate the flow faults and to target the design related info. I can say procedure file. I can say synopsis procedure file, or in that certain information related to the DFT are included. So this file actually when I need, so when I'm doing the ATPG, I need to, as a input, I need to take this file and this netlist as well in order to do the ATPG. Okay. After scan insertion, the parallel another topic is I'm not going into the directly ATPG, but another this is also very important parameter. We can say OCC. So OCC on chip clocking, why we need? So first one is when we are doing 8-speed testing. Yeah. Any questions?
Yeah, sir. One question in the chat box. that what information library files have in a scan insertion.
Okay, so here, right?
Yes, yes.
Okay, so here in a library file, normally it's a DB file we are using. So it is a hard coded, but it has like standard cell info, we can say. It has all the parameter, like let's say there is a different gates. So in gates also, like certain parameters are there. It's a timing related timing related information is also there, because let's say in D flip flop, so there are n number of the D flip flops are there in the library. So it has different parameters. So which D flip flop I need to use. So normally during synthesis, everything logic is replaced. So certain checks needs to be done during the synthesis, because the same library we are using here also. Whatever the library is used during the synthesis, the same library I need to use here. It says normally we can say standard cell information only of all the cells. I mean, it's a inverter cell, all the different logic cells, we can say. And also sometimes it's a timing related information is because the same library like we are using for the simulations as well. So if we are performing the gate level simulation for the different corners, then we need to based on that those info, like it will interpret this cell is used for this cell have these specifications. So we can say the standard cell specifications are there. Okay, on OCC, this is very important actually for DFT. So first thing here is like why we need OCC. The answer is we can say in my design. Let's say if I wanted to test at speed testing, okay. Why we need okay, at speed testing means I wanted to test certain logic with actual functional frequency. So at that time I need to have the actual launch and capture cycles. So in Stuckit, what happens, we are not doing any transition, just we need only one pulse. Here you can see the Stuckit. So I need only one pulse, and this pulse might be at speed, or it normally shift is also fine at shift speed. Okay, so if I wanted to test Stuckit fault, only one pulse capture pulse is enough, because I am placing the data in a flop with shifting, and directly I am doing the capture at any frequency, because here there is no transition. So I'm not checking in delay related issue here. My intended is only checking logical faults, either it's stuck any 0 or 1 due to some manufacturing defect. But in transition, what happens, I need to check specific fault at speed. When I'm saying at speed, so I need to have launch pulse and capture pulse both at speed. Launch pulse means let's say, okay, if I wanted to try this node for TDF, okay, so what I need to do here, initially if I place 1 here, and this is also 1, okay, so my output is 1 in AND gate. If I make it transition 1 to 0, so what happen, either 1 to 0, at that time my output should be 1 to 0. It should go 1 to 0. But what happens if due to some interconnect and some internal delay of this gate, if my output is going 1 to 0, but it is little slow when the capture cycle is happens, and before that if it is not reflect, then here we will have wrong capture, and wrong capture will shifted out at a wrong output. So what happens here, we can say my chip has a transition issue, my chip is slow to rise or slow to fall. So this kind of the issues, when it is have, we need to have launch pulse also at speed, and capture pulse is also at speed. So two pulse I need. So once I need a two pulse, we need to have some OCC structure, some clocking structure. It can give the different pulses when the scan enable goes low. So during it's not only two pulses, in certain cases 3 pulses is also required, 4 pulses, 5 pulses, 6 pulses. So OCC is required in order to generate different pulses. So normally TDF have 2 pulses, launch and capture pulse. So now what is the internal structure? So all the companies have their own hard IP for this OCC. Here it's very simple diagram is there, but it's very complex IP when different vendor have. So ultimate goal is when the scan out goes low, it should throw 2 pulse. So for that the mechanism is here is the muxing is there. So we have like main clock input, we can say is a fast clock. Fast clocks normally comes from the PLL. So or it might be sometimes it is there is options to have this clock from the top, external clock. So it depends on the design and like how the requirement is there. So PLL is again one IP, so it will generate the fast clock as expected based on the PLL programming. And once the PLL programming is there, we have clock at OCC input till this point. So once the PLL is a free running clock, here we can see in this wave, it's a free running clock. So it is always input to this, and this is the clock getter cell. So clock getter cell like it's a kind of enable. So it says enable. So in clock getter also like there is a one latch, AND get, and OR get output. So this is like clock getter one cell, and once based on the enable, it will here enable out the. It will enable for the sometimes CG out here you can see. So based on the PLL clock enable, how much time it is on, it will allow to pulse to out here. And once the pulse is out here, and this selection line is already scan enable. So scan enable is already 0. So it will allow propagate to clock out during when the capture during capture phase only. That means scan enable goes low. So here this is the like basic structure of this one. So PLL clock enable is again generated by sync flop and shift register circuitry. So based on different configurations, like it is the based on the enable width, it can create the n number of the pulses. So this is very basic structure and of like OCC. So like in our design, when I'm saying TDF, I'm talking about top level. So there are many OCCs in our design. It's not only one OCC. So based on the number of clocks, we have number of OCCs. Let's say my design have 10 clocks, 10 separate clock. So I need to have like 10 OCCs for different frequencies. I can't use the single OCC. So OCC placement is also important, like for DFT consideration. Okay. Any question in OCC side? Okay. On ATPG, yes. So now the next thing is we can say ATPG. This is a very important stage in a DFT, because here when everything is ready, now the pattern generation needs to be start, we can say. So it is again always start with ATPG flow, means now my design has already MBS insertion is ready, scan insertion is ready, and all the required output is ready, and now I need to start for ATPG. So ATPG is also like certain things needs to be do before starting. It's not like directly we can start with the pattern generation. So here also we need to do some DRC checks and built model we need to do. Okay, so here I'll go through step only. So here we already have scan insert and netlist. So in ATPG environment, I need to do the read netlist, read libraries, and based on that it will create the, after that the next stage is the building the model. So what happens in the during the build stage, so now we have a design and library, so it start building the virtual design, we can say, build the netlist. So it has all the information of the nets, and it will create kind of one build model. So now this build model has all the information related to the, we can say, it's a create a flat model, uh, and it has all the information of the nets and the primitives, all the gates. So now here in the build model also certain DRC needs to be checked. Certain DRCs are occurs. If few of the DRCs we need to fix, and few of the DRC we can actually wave, so we can go further for that. The next one is the perform DRC. This is very important stage here, DRC checks, because as I said before some time, in post insert DFT, if I not check any DRC, then definitely I need to fix it should occur in ATPG stage. So once DRC comes here, I need to fix this DRC first, and once the fixing those DRCs, like we can then we can go for the ATPG side. So here
One
different,
question
yes.
in the chat box: difference between TDF and SAF.
Okay, so these are two different fault models. In the TDF, okay, in Stucket we are only like okay, let me go to here. Okay, Stucket means what? Only consider this AND gate only as of now. We don't have any circuits, any other circuits. So Stucket means here I have two input AND gate, 1, 2, and 3. The third one is output. So total we have 3 nets, 3 pins, we can say. So either now if I wanted to generate vector, so I have 3 nets, 3 pins. So either A is stuck to 0 or stuck to 1, B is stuck to 0, stuck to 1, and output C, let's say, stuck to 0, stuck to 1. So there are 6 possibilities are there. So I need to generate a vector for in such a way that it could cover only stucket fault. Stucket fault actual defect might be different, but our as of now, like what we are trying, our intended, our vector generation is for the stucket. So here in stucket we don't need any at speed pulses. I mean the frequency of the operation would be capturing would be happen at any clock frequency. So stucket I can say there is no any 8 speed pulse is required. But when I am saying transition, if okay, in other words, what I'm saying, if suppose let's say my gate is working fine, if I'm applying the stucket vectors to this and my gate is working fine, so does that mean there is no issue with this gate? No, right? There could be an issue with this gate. So what I need to do, I need to go for another fault of testing. Stucket is pass, that doesn't assure my gate is working fine. So what I need to do, another fault testing, that is we can say transition fault. Because why I need to do transition fault? Okay, first let me tell you what is transition, then I can tell why. Okay, in transition fault what happens, there are two possibilities. Transition, as a name indicates, transition fault. So data at input is transist 0 to 1 or maybe 1 to 0. So normally what happens in actual functionality of this chip, in functional mode, our data is continuously changing based on our whatever the operation, functional operation is happening. So if there is no stuck at fault, but my gate is slow somehow, or my interconnect length due to this something like delay is more, we can say basically it's a delay testing kind of. So if delay is more, what happens, if 0 to 1 transition is happen here, so output also should reflect the same speed, or it should be in a required range. If 0 to 1 here happens and output is also 0 to 1 happens, but after some times, before our, like when we are our clock capture is happening, at that time 0 to 1 already data is 0, it's not reached to the 1, then it will wrong capture here. So what we can say, here wrong output will propagate. So that does occur errors. So based on the errors, what now we reverse trace that, but this gate is having some issue. And what is the issue? So delay is more. So transition is not happening properly. So there could be in real scenario, what happens, the gate is working at a 8 speed frequency and 8 speed we can say in real environment, in functional verification, functional vectors, or we can say in the functionality. So data is continuously changing, and here the clock is with 8 speed. 8 speed transition will happens in functional. So if in order to make sure this gate having no issue, we need to do transition is must. So like is there any still further doubt, or like or not still like have some query? Can you?
Sir, just one
Yeah,
question.
Corsair, is it clear?
Yes, sir, got it. Thank you.
Yeah, sorry. Yeah, so it is clear.
Oh, okay, thank you. Okay, so again on ATPG side, here we reach here. So in the perform DRC stage, so DRC is very important here. So let's say sometimes what happens, everything was clean on the stucket side, I mean insertion side, during scan insertion, but here some DRC is again pop-ups. So those DRC might be related to some valid DRC is also there, or sometimes due to some constraints we are using here during reading the netlist, and we need to put some ATPG constraints in order to perform ATPG. So due to those constraints, some DRCs also occurs. So we need to fix those DRC before generating the patterns. So once the patterns like DRC is fixed, the next step would be run ATPG. So once the run ATPG is done, run ATPG means either it is we are targeting for specific we can say fault. Let's say this is like I'm right now I'm targeting stucket fault, so I need to do only run ATPG for stucket. Everything I need to do this many steps, then I need to here put some certain commands for the stucket, and then I need to start the pattern generation for stucket. If I wanted to do TDF, again I need to do the same steps. Here certain things I need to change in a scripts, and I need to start for the TDF. So this is the flow for the like ATPG. Once the run ATPG starts, tool engine will start generating the patterns. So once the patterns are generated, we can review the test coverage. So test coverage is it's a parameter, we can say. There are certain targets like we need to achieve, then and then my design would be, I can say it's tape out ready. For stucket normally we need to have 99% target coverage, but for TDF it's depending on design and depending on clients. So normally the standard is 90 to 95% for TDF, target coverage. If coverage is not coming as expected, so we need to review the test coverage where the coverage is lost in certain design. Let's say my design having 50 blocks of certain blocks, and one of the blocks I am having very less coverage. So I need to review those, why it is less coverage. Then based on the coverage, where is the certain points I can improve. So those kind of the analysis first I need to do, and based on that, like again we need to rerun the ATPG. And once we are rerunning the ATPG, and once if the coverage is expected 99%, then we can say the save the patterns and go for the next thing. So what is the next step here is, okay, next step would be simulation. Here I'm just I have not
One question is that industry is currently using which ATPG algorithm? Can you able to like in our MTech course we taught
D algorithm normally, right? But there are what I remember, because there are two currently, or three companies, three vendors are there, but mostly like Cadence, Synopsys, and Tessent, right? So their engine might be they use like PODEM, or there are very advanced PODEM some algorithm. So
so D algorithm is still
D advanced. There are many things like advanced, I guess, but even I'm also not sure on this,
okay.
because nowadays I have and during research phase, like we need to do, but as of now, like I can't focus on like algorithm side.
Right. Okay.
Yeah. Okay, so this kind of the reports are normally printed. It shows like some patterns are generated, this many faults are detected, these are the still active, redundant AU about, test coverage is this much, and process time. So this is the one like sample I can say. So let's say in like 774 patterns, I'm seeing 99.97%, but normally I'm not seeing anywhere. But this is like one I can say sample, but normally our target is 99%. And this is the Synopsys output report, by the way. So here like the fault category is DT, PT, UD, AU, ND. So these are different fault categories are there. So our the test coverage equation is mainly depends on detected fault by the total fault minus UD fault. So this is the equation which will give the test coverage. So yes, so normally for us as a DFT engineer, the challenging part would be ATPG untestable fault. So why these faults are untestable? So those is the main target to focus. If we can focus more on ATPG untestable faults, we can get higher coverage, because it whatever the fault covered from 31, let's say if I can cover 31 to 15 fault, so again it will got added to the detected fault, and I can get little higher coverage. So AU is the culprit, AU and ND during DFT. So these two category mainly we need to worry. Okay, any questions here?
Participants, are you having any question? Yeah, the core madam is asking, sir, the example of untestable and undetectable faults.
Example. Okay. Undetectable faults is something, okay, I can currently I don't have any gate level circuit or something like that.
Okay.
But I can tell you what is the difference between these two categories. Undetectable is something like in any of the cases, the tool is not able to cover. It's undetectable, and tool is not able to target those kind of the faults. Let's say some boundary related faults, input pad related faults, or output side pin related faults. Those are we are not able to cover up using our DFT patterns. And if something and those kind of the faults also not we can say make any failures on the chip, functionality failures on the chip. So we in other words we can say, I think we can go with this undetectable faults. Yeah, but one thing we need to make sure this number should not be very high here. For example, here 134 is there. Okay, so if my total number of faults are 16, okay, 160k, and 134 is it's 0.0001% something. So I think I'm not worried about this faults, because in any circumstances those faults are not able to target. It might be in UD also there are certain categories are there, because those are due to tide something, or let's say okay, let's say this is the OR gate is there, and this input is controlled by this flop, but another input is constrained, or sorry, tied somewhere in a design. Tied in the sense either it is driven by some test mode, because test mode is always one during testing. Otherwise if it is zero, then circuit would be in a functional mode. So those kind of the faults, if this is already tied one, then my OR gate output is always one, irrespective of this. So this, the whatever the faults comes in this outcomes, or this downstream logic here, it will comes as a UD. So I think this is enough example, I guess. So UD. So I cannot test those fault in any circumstances. Another thing is ATPG untestable. It does, as a name indicates, it is still testable, but due to some ATPG thing, ATPG constraint, or some condition is happening in such a way that the tool is not able to detect those faults and not generating the pattern accordingly. So here comes the issue of the controllability and observability. So somehow why it is not able to test. Sometimes what happens, there are more combinational logic, and there is very, we can say, the flop or sequential elements are very less in a design, let's say. Then it is very difficult to set the each and every node of the flop, and those flop output reflect to the and it is very difficult to observe the output on a capture flow. So there are certain cases we can't test or we can't generate any suitable vector. Tool is not able to find any suitable vector for those things. So in that case, what we can do? So in that case, yes.
Both are UD and untestable. They are tool limited faults.
Sorry, UD and
This
your voice is
untestable
little
faults,
low.
both
Madam, please
UD
speak
and
loudly.
untestable faults.
Yes.
They are tool limited.
Tool
Limited. मतलब दोनों टूल से they are not being detected by the tool.
Yeah. See, okay, this report is already generated by tool only, but the thing is, tool means okay, undetectable faults is never be detected, never, anytime. So whatever the number is there, it is already it is okay, on test coverage calculation, these faults are not creating any problem. So it is already out of the calculation, test coverage calculation, undetectable. But when I'm saying ATPG untestable, so this is also like a part of test coverage, and we need to worry about this ATPG untestable, because those faults can create a problem to the chip as well. And also we need to like uh, try to cover as many we can try on vector generation. So once it is EU, if we fix those issue on by analyzing the faults, then when we are running the rerunning the ATPG, like if something like, let's say now it is reduced to 31 to, let's say, only 10, the remaining faults are already covered. So that will be good for design as well, and we can say like our pattern quality is good compared to the previous scenario. So like we need to do rerun ATPG also many times in order to get 99% coverage.
Thank you, sir. Thank you, sir.
So here normally EU is due to constraints, or as I said, very too complex combo logic is there, and tool is not able to. Sorry, just a second. Excuse me. Sorry. Okay. Okay, so another parameter here is also like fault coverage. So those two are like fault coverage, but normally is a DFT need to worry on fault coverage only. Sorry, test coverage. So here what we can do? Okay, okay. Now I forgot. What is the solution to this? AU and ND. ND is not detected. So as of now, tool is trying to do efforts to detect those, try to find some vectors which test those specific faults. But as of now, it is no success. So that's why it is kept in the not detected. So what we can do? So we can identify certain region, and based on the region, what we can try is we can do analysis, and based on the analysis we can put some test point as well in order to get more controllability and observability. If based on the test point, like we can once we insert the some flops or test points, like we can get some output of those internal like let's say a very internal node to some those flops, and we can detect those faults. Okay. Yeah. Okay. Another thing. Okay. Before this ATPG, once the patterns are already generated, so next step would be uh, verification of those patterns. So patterns are generated, but like how it is actually behaving on silicon. So we can't directly test on silicon. So we need to like verify those patterns on our GLS environment, gate level simulations. So where we have full designs, netlist, and we need to apply those vectors on those netlist in order to verify those patterns. So once the patterns are passing, let's say, then and then we can confirm the quality of the patterns. So this is very must step, we can say, after TPG. If those are passing and coverage is hitting, then and then the design is ready for tap out. If patterns are failing and coverage is not meeting, then tap out will not happen. Okay. Any questions here still? Okay.
No, sir. Right now, there is no question in the chat box.
Okay. Okay. So Next topic I can say JTAG and internal JTAG. So nowadays, people on SOC level mostly implementing the IJTAG strategy. So this is like initially we had a JTAG. So tape controller will control the core logic through some boundary registers. These are the boundary cells, and based on the configuration, either we can place the data from IO, and so for the testing purpose we can set the mode and testing, and from TDI to TDO we can check the output. But here, so this is where I think most of the people might aware on JTAG standard. But here what happens, so in IJTAG, internal JTAG is a 1687 IEEE standard. So on SOC, most of there are nowadays it's n number of IPs, and many IPs are from third party vendors. So let's say memories are coming from some different vendors, like PLL IP is coming from different vendors, UART is coming from different vendors, and there are other different IPs related to like SERDAS or any other graphics, all different IPs coming from different vendors. So in order to integrate all on a chip, like we need to have IJTech. So it has capability of plug and play kind of, so we can all the IJTech instrument here I can see, you can see instrument. So each instrument we can consider as each IP. So there are n number of instruments are there. Memory based logic are also there, memory for the memories. So all these instruments are connected through the TDRs, test data registers, and TDRs is connected through the SIPs, and those SIPs are again controlled through the tap controller. So those SIPs are kind of enable and disable mechanism. So either we wanted to connect this TDR or not. So if SIP is enabled, then we can control is a part of this TDR chain. So TDR chain is a part of our scan chain, and we can program through tap, from tap to TDR. So ultimately our objective is we wanted to place some values or programming values on, or place some values on this TDR, and we wanted to read also those values from TDR. So this is like easily we can access those things by tap based on SIP programming. So TDR programmings, let's say I have my PLL IP. Here we have PLL IPs. So PLL has some reference frequency, reset, and other n number of inputs are there. So those inputs are have different control through some TDRs, test data registers. So if I wanted to test this PLL, what I need to do from the tab, I need to enable those SIP sequence are there, and I need to program. Let's say this is 130-bit TDR, so I need to program 130-bit shift register, and those register are again provide input to this PLL IP, and PLL IP will generate some outputs, and output is again goes to some TDR, and we can read back to the TDO. So like this kind of the structures are placed in SOCs. So if IP is changed, what happens, like let's say there is update in IP, so they can easily remove the IP and put the new IP. So it has a similar TDRs only. So it's very easy to access through IJTech, internal JTAG. Similarly, memory also, like either we wanted to enable this memory or not, so we can program accordingly. Let's say other logics are also there. Those logic are again functional logics are there, and functional logic is again connected through some wrappers, and those wrappers are again controlled through the TDRs, and TDR is again controlled through SIPs. So there are a number of SIPs, and like in order to access there are equal PDL flow is there, instrument custom language, and PDL flow is there. So those as a mentor is easily supports these IJTech mechanisms, and initially only this IJTech architecture needs to be implemented.
So I'm having one question.
Yes.
So as per my awareness, normally this JTech is used for boundary scanning to check the IOs.
Yes.
So
Yes.
using this JTech, can we able to check the functionality of IP also?
Functionality of
IP, like PLL you have considered.
yes. Yes. Through JTech.
Yeah.
No, IJTech we can do.
Okay. Using iJTech, we can verify the functionality also.
Yes, functional, because in PLL what we do, PLL we do PLL is a independent IP. Okay,
Okay.
so there's suppose let's say PLL is already verified by someone.
Right.
Okay, so we need to just plug and play in our environment, in our SOC. So the purpose of the PLL is we wanted to generate certain frequency. Let's say 1 gigahertz if I wanted to generate as an output. Okay, my input reference would be, let's say, 100 megahertz. Okay, and there are certain bits like inside the PLL, as we know, like VCO and low pass filter and phase shifter, everything is there. So we are not worried about what is inside the PLL, but output, how many inputs we need to provide as an input. There are 120 or 30 other inputs are also there. Reset, then programming inputs, like how many bits I wanted to, because 1 gigahertz, how I can calculate. There are some certain VCO is there, right? So VCO has also some inputs. So those inputs are also connected by TDR. Like we need to program through TDR, and also there are feedback and factor, like feedback divider circuit is also there. So those also we need to program at what divider we want. So those kind of the TDR bits, like directly we can access through outside, and we can program that, and so PL try to generate the frequency what we need. And so accordingly, once the PLL has generated the frequency, we can also like verify those things through simulation as well, because simulation also we are applying the same vectors on chip, on DUT we can say, and we are measuring output, either PLL lock is happening or not, what is the frequency is coming, is a 1 gigahertz only is coming, or it's 990 is coming, or 900 is coming, like. So those things like we can do, and also we can check either internal all the values reset is coming fine or not. If reset is not coming, then our PLL will not reflect as expected. So there are certain checks like we can do using this also.
Okay.
And okay, yeah, so there are certain advanced DFT techniques. I'll not talk on all the techniques, but this is very basic techniques, codec, compression techniques. Why we need a compression? Because let's say in my chip I have 1 lakh flop, 100k flops. Okay, and I have only one IO, top level. I have only 2 pins are available for DFT. So what I can do, one is scan in and one is scan out. So I need to stitch all the flops in a design in one chain. So what is the test time? So test time would be, let's say my clock cycle would be 100 ns. So 100 ns into 1 lakh. So that would be my test time for shifting and shift out. So my test time is increased, then the pattern size is also increased. So there are certain limit on ATE tester side. So tester is very limited memory in order to fit the all the patterns. So we can't give the full mode patterns because to ATE, and the test time is increased. Test time is increased. That means the cost of the chip is increased. So now what we can do in order to reduce the test time, there are tool is or Synopsys or maybe Mentor or Cadence have different uh, technology, or we can say IPs or hard macros or techniques are available to define reduce the test time. So there are codec, share codecs, and here in the last I put one of the latest techniques which supports synopsis. Actually, this all are as of now I kept from the synopsis only. Mentor has also different techniques, EDT based flow. But here the ultimate goal is to reduce the test time. Another thing is power. Power in the sense shift power, capture power. So power is very important parameter. Third one is airdrop. So these parameters needs to be take care like initial stage of the insertion as well. So this architecture and techniques defined during the before the starting the insertion only. Then and then like accordingly we need to work. So one of the technique we can say compressor and decompressor codec. Codec, what happens here? Decompressor. It's kind of the decompressor. So here certain logic is there. It will like based on our configuration, we can partition the one chain into the sub chains. We can say n number of the short chains, and again we can do the compression, and we can take the output on output side and ATE. So here the test time how it is reduced. Let's say I have 100k flops in one chain earlier, but now I am putting 1000 partition. So now I have those kind of the 100 chains are there. In each chain I have 1000 flops. So my test time is almost reduced by 100 times, and I can like save significant amount of the ATE memory as well. So that we can these are the one of the techniques, basic techniques we can use for the insertion. Another technique is area is also sometimes important. So and also pin is also limitation, pin limited. So here I can say two cores are there. I have inserted two cores in two bigger block in my SOC. There are two partitions are there, and I have inserted two codec, one codec 1, codec 2, and for codec 1 I have 3 pins, and for codec 2 I have 2 pins as an input, and output is also 3 and 2. But here what happens if I am using the sharing codec concept? If I have like pin count limitation on design side, let's say I have only 3 pads, 3 IOs are available for DFT purpose. So I need to do the pin sharing concept. So there are certain multiplexing techniques here are used in order to bifurcate sharing this codec 1 and codec 2 for the different cores, and sharing compressor for each. So these different methodologies are need to be architect before the starting the DFT. The third one is latest one, one of the high I have used in one of my recent design. This is the DFT ultra compressor. Here my constraint was I have only one pin as an input, and customer has asked us to implement the DFT architecture. So the client there only I have one pin for the input and one pin for the scan out. So this is only decompressor portion, I can say. I haven't put here compression processor. Compression would be similar to this. So this is only, we can say, is one part similar to this. This is the one part, decompressor side. So decompressor side I need to use the serializer, SerDes serializer. So it has certain bits, and in order to here, okay, one limitation is this is pin count here. Another another point is another limitation was, I can say, power is also one of the very crucial here. So it's a low power design. So I need to do low power design. Keep in mind, area is also, this is the one of the design area is also very important. They want area is also less, power is also less, pin count is only 1. So it is very difficult us to define the architecture. So I implemented this shift power controller chain, which controls the internal change of like output of the decompressor. Let's say this kind of the outputs are there. So it has some gating logic here, and gates are there. So based on whatever the data applying here, it will go through this decompressor out, and it will enable or disable the specific chain only in order to reduce the power. So at a time, based on this value, I can say like group of 333 is there. So if I set certain parameter during ATPG, uh, the tool will try to understand those commands and generate or fill out those bits in such a way that it will enable or disable specific chains. So if specific chains are enabled or disabled, let's say only 3 chains are enabled, so I can save the power of remaining during shift. So those will be target next time. I mean, in one pattern, let's say only these 3 chains are instantiated or excited. So in next pattern, another three like that. So I can control the power as well. Even here serializer is used. So here I can get the multiple inputs as from the data. So those are again feeding to the decompressor. So this is also like help us to like use the single pin. So similarly, output side also like decompressor is there. It again like compact all the chains, and output is again goes to the deserializer, and again deserializer output is goes to the final SO scan out. So this is the like one of the techniques recently I tried. And normally like coverage improvement, as I said, like OCC is important role. Then techniques are there: LOS, LOES, LOC. Normally we are using LOC, launch on capture. Launch on shift and launch on extra shift is also another techniques. Test point insertion I already like uh, try to cover in during the fault analysis. If AU is still we are not able to detect faults, we can try for the test point insertion. And IJTX definitely is advantage if we enable disable the specific IPs. If we don't want it to include in a chain, or we can save the power as well for those IPs. Let's say those IPs are like hard macros and very well tested, and functionally it is covered, then we can exclude from the scan as well. There are certain techniques like SDD faults we need to nowadays it's become very critical. Cell level ATPG is also there. I can we can generate the patterns, because there are certain flops. Flops are working as expected, but there is inside the flop some defects are there. Then it is like very difficult to catch. So that's why like cell level ATPG comes in the picture. So this kind of the techniques normally we are using depending on the requirements. Okay. So yeah, I think yeah, that's it from my side. So any questions here?
Any questions from participants? So I think there is no question, sir, from the participants.
Okay.
So thank you very much, sir, for
Thanks.
delivering such a extremely useful talk on DFT. In your talk, you have covered, I think, all the aspects of DFT, starting from DFT insertion, controllability, observability, scan insertion, boundary scanning, use of ATPG, etc., etc. So I am sure that all the participants are benefited from your talk. Thank you very much, sir, again,
Thank you.
for sparing your valuable time with us. Thank you.
Thanks. Thank you, everyone.
Yeah. Dear participants, now as per our schedule, Next session will be on 12:30 p.m. It is on FinFET, and the talk will be delivered by Dr. R.A. Thakkar sir. He obtained his PhD degree from the MTech as well as PhD degree from the IIT Bombay. He is having very vast experience on nanoscale devices like FinFET. So as a coordinator, we humbly request you to join sharply at 12:30 p.m. Fine. So we will meet once again at 12:30. One comment is there in the chat box made by Yogesh Tiwari sir. Thank you, Bhavesh sir. It was a great session. Yeah, truly, it is a great session.